the irrigation panel that should have started at 17:45. That will actually be combined with the panel on farming practices. There are very strong relations between them. And so one more time, irrigation that should have started at 17:45 will actually be moved to farming practices, which will start just after the keynote at 9:45 at the Universitätsspital Rosen 2. If the Okay, now the real business. It gives me yet again great pleasure to introduce to you Marc Rosen as a keynote speaker. Marc Rosen is a professor of mechanical engineering at the University of Ontario Institute of Technology in Canada. He was Dean of the Faculty of Engineering and Applied Sciences from 2002 to 2008. Dr. Rosen was president of the Engineering Institute of Canada and president of the Canadian Society for Mechanical Engineering. He's a member of the board of directors of the Oshawa Power and Utilities Corporation. He served on the editorial boards of several journals and as an advisory member of several leading international conferences, including, of course, ours. He is, most interesting for us, editor-in-chief of our journal Sustainability. He has held over 70 research grants and contracts and published around 600 journal publications. And he is fellow of the Engineering Institute of Canada, the Canadian Academy of Engineering, the Canadian Society for Mechanical Engineering, the American Society of Mechanical Engineering, and the International Energy Foundation. So, Marc, thank you very much for agreeing to do a panel. Thank you very much for your tremendous work also for this conference and for sustainability. The floor is yours.
Thank you very much, Max, for the kind introduction, the kind words, too many words in fact, but it's wonderful to be here. I want to thank you and the University of Basel for hosting this event and having me here. I know it's a lot of work to organize the conference. I want to doubly thank you for all your efforts and the team that helped you. And I also want to thank the Journal Sustainability and MDPI, Shukan Lin, the president of that organization, who very much was the inspiration behind having this conference. This is number 5. The first 4 conferences were in fact virtual conferences online without physical participation, but in fact allowing a different type of participation. People from all over the world who could not travel were able to participate. And that's great, but we also need the physical interaction quite often, so an event where we actually show up is really helpful too. I want to talk to you today about sustainability from a particular aspect, one aspect that I've been heavily involved with in my research side and my teaching side somewhat, and that is sustainability and its relation to net zero energy buildings and an extension of that, net zero energy communities. I'll talk about what I mean by those precisely as the presentation goes on, but I'll only mention right now that it's not a minor topic. When it comes to energy, in Canada I know energy use in buildings, and the building sector is responsible for about 1/3 of the nation's energy use. And I heard in a presentation here yesterday globally that number is more like 40%. 40% of energy makes its way into the building sector. So being able to knock down energy use in the building sector can have a very significant impact on reducing energy use, and that can certainly help us move towards sustainability. So the motivation, why I want to talk about this, which in a very strong sense gives an outline of what I want to talk about, is shown at the bottom here. Sustainability, don't need to say how important it is to a conference like this, but I don't mind repeating it's something that I think is an admirable, important goal for societies to strive towards. Energy sustainability, where I've focused a lot of my attention, is something I believe is a really big component of overall sustainability. In many ways, if you could knock the energy issues out of the world, energy availability and abundance for everyone who needs it, I think we'd resolve a lot of the issues about sustainability. If we could get rid of the environmental issues associated with energy use, economic issues, geopolitical problems that stem from energy resources and their unequal distribution, we would really make a big step towards sustainability. Buildings and communities, as I mentioned, play a big role in the energy sector. A different type of role in different countries. When it comes to Canada, the heating side of buildings is much more important than the cooling side. Although the cooling side in summer in Toronto, where I'm from, and that's the skyline of Toronto. The summer in Toronto actually has a higher peak electrical use due to air conditioning because of the heat and humidity than in winter, but the winter heating dominates. In other countries, cooling dominates, and we have a mix. Buildings and communities, so I show Toronto's skyline not only because I'm from there, but to mention it's a large urban center, 7.5 million people approximately in the greater Toronto area. Energy use, of course, you can just imagine looking at the picture, heating and cooling the buildings, lighting the buildings, the transport corridors running from building to building and out to suburbs where people might live, but then commute downtown. The electricity to drive the lights, to drive the machines and offices, to drive the industries that you don't see here because they're further back. All very important. But that doesn't mean that rural energy use isn't equally important and has its own set of issues. So sustainability, I won't dwell on it. What I will mention is it comes up over and over and over. One area that was very interesting to me where its importance was highlighted was in the organization which I am a past president of in Canada, the Engineering Institute of Canada, which is a learned society collective. The president, it doesn't have individual members, rather the presidents of the mechanical engineering organization, civil, chemical engineering, etc., are all on the board of the Engineering Institute, and we deal with cross-disciplinary issues in engineering. It's been around for more than 100 years. We recently went through a visioning exercise, and the vision statement in a very succinct form is shown here. I've highlighted the word sustainable. So out of the 3 adjectives that made its way there, sustainability was front and center as one of the most important. So engineering for a prosperous, safe, and sustainable Canada. And the words go on to say, of course, and using that to help beyond Canada's borders. It's also a very multidisciplinary field. I think we see that reflected in the breadth of papers and topic streams that were just in this conference alone. I see it every day through the journal Sustainability, because as editor-in-chief, I see all the papers that come through. And the breadth of papers utterly staggers me. The different ways sustainability is interpreted by different communities utterly educates me every day on a different twist, a different angle, a different interpretation of what sustainability can mean, and ways people can take actions to move towards sustainability. For those who aren't that familiar with the journal, of course, it's an international open access journal. It's been in publication since 2009. It publishes quite a few papers per year now, and seems to be attracting ever-increasing interest. I'd encourage you to submit your papers to the journal that you presented at this conference if you're interested. Moving towards energy sustainability, the focus of where I do a lot of my work and kind of the background premise of the work I want to talk about on net energy buildings and communities is where I want to go now. So I had a question. How do we define energy sustainability? When it comes to general sustainability, I think most of you are familiar with the definition that came out of the Brundtland Commission and the definition that's kind of stayed with us for a couple decades, since the mid-1980s, a development that allows the present to meet its needs, but not impacting negatively future generations and their ability to meet their needs. But then other definitions have come up since then. I heard several presented at this conference. But that's sustainability generally. What about energy sustainability? Checked the internet. I couldn't find anything. I checked Google and was shocked to find I couldn't find a definition there. I don't know what to do when Google doesn't give me an answer anymore. So I had to actually take out a sheet of paper and say, I'll figure one out for myself. Like it or not. I tried to be very short in words, so I simply said, well, it's energy sustainability is the provision of not energy, but the services that energy provides. The services. I want that projector to be shining light. I do not care if it's running on coal, electricity, sunlight. I just want the service. What the energy that drives it is a background consideration. People care about the services. A heated building, a lit projector, etc. So I want the provision of energy services to people in a sustainable manner, in a way that it does not impact negatively on directions towards sustainability. And I thought I was really clever. And I presented it to a conference, and somebody stood up, a linguist, and said, no way, you can't do that. I said, what's wrong? And he simply said, there it is, that you cannot define this term using the same word. That's a circular definition. It means utterly nothing. It's garbage. Okay? You're right, I'm not a linguist, I'm an engineer, and I apologize. So I have to go further and say, what do I mean by in a sustainable manner? And I added, certainly sufficient for the necessities. For 20 years, based on existing knowledge. But with advanced technologies, people in the industry tell me breeder reactors should be able to stretch that base out to maybe 1,000 to 1,500 years, because right now we use only a small percentage of the energy in uranium when we fission it. There's a lot more in the spent fuel that we don't use. That can be reconverted to a fuel that stretches lifetimes of the reserve to more than 1,000 years. That starts to fall within a pretty sustainable frame and definition. Of course, it has many benefits. There are negatives like the concerns with safety, but on the benefit side, no carbon dioxide emissions, no real contribution to greenhouse emissions. Okay, so sustainability requirement for energy number one, let's use sustainable sources of energy. A more subtle distinction is to use appropriate energy carriers. Fossil fuels are somewhat unique. They are not only sources of energy, but for the most part, they can be carriers. We can transport liquid oil, we can truck coal, we can transport natural gas through a pipeline. The source can be the carrier. Many other forms of energy we can't. Sunlight. It shines where it shines, and we use it there, or you're not going to set up an array of mirrors to reflect it throughout communities. We convert it to something. We can convert it with photovoltaics to electricity. We can also use sunlight to split water thermochemically to produce hydrogen that can drive vehicles, like shown in that hydrogen vehicle at your right. Hydrogen and electricity are not sources of energy. They are convenient means of convenient currencies, ways of transporting and getting energy from one point to another, perhaps storing it and using it more effectively. The importance of energy carriers then is very much tied to the fact that the appropriate energy carriers needed to liberate or allow us to use certain energy sources that otherwise are very difficult to use. Hydrogen, you hear a lot about a hydrogen economy, potentially, and they always say it's just around the corner. When it will come, and to what extent it will come, I don't know. But the main idea behind hydrogen is a lot of things can run on electricity, but certain other technologies, like vehicles, for instance, might run better on a chemical fuel. Hydrogen is a hydrocarbon that has all hydrogen and zero carbon, hence no contribution in terms of carbon emissions. So it's viewed as a substitute for fossil fuels that really, for the most part, can combust or electrochemically be converted to electricity at high efficiency, but avoid carbon emissions. Third requirement for energy sustainability, increased efficiency. That kind of is obvious, but I put it in there because it shows up in so many dimensions of engineering and technical work. And I mean efficiency in a very broad sense, or I'm not at all comprehensive. So by increased efficiency, I mean the obvious: make devices more efficient, make that projector at the back of the room shining light here more efficient so it uses less electricity than it needs to now to shine the same light. But you can go beyond that to system efficiency, like a large complex power plant with 100 to 200 devices in it, make the overall complex more efficient. Same idea extrapolated to larger numbers. I would also include appropriate energy management, looking for periods when energy is demanded, when energy is supplied, and if there's a mismatch, maybe implementing appropriate storage. That would be important for wind or solar energy, so that you drive up the overall efficiency and you make the utilization of certain resources possible when they would otherwise not be possible. Matching supply and end use is also a type of efficiency. That leads to a lot of work using tools like exergy analysis or the second law of thermodynamics, where I do a fair bit of research. For example, space heating. It's cold in winter here. You might want to heat the room. You heat the room to maybe 22 degrees. And you could use electricity to do that. You could burn natural gas to do that. But those are very high-quality energy forms used for a very low-quality task, simple heating at 20-some-odd degrees. You could, on the other hand, use low-temperature, flat-plate solar collector thermal energy, or waste heat from local industries that would otherwise be rejected to the atmosphere through a district heating network. So you can look for temperature matches that are more appropriate. If you need low temperature, 20 degrees, maybe there's a 100-degree source available. Try not to use something like electricity or natural gas that can easily produce 1,000 degrees. Metal, drive industrial processes. That's a hidden type of efficiency that we can achieve. Integration of processes. Look for ways of integrating processes so the waste from one process that would otherwise be discarded but potentially could be used as an input to another. Find a way to link them up. Integrate them so that wastes get reused where there is a useful buyer of it. Waste heat that I just mentioned in the above example is one example. You can cascade heat. You can locate high temperature industrial facilities next to facilities that require low temperature heat. So the waste heat from, say, a metals refining plant gets used in a plastic processing plant at lower temperature. The waste heat from the plastics plant could be fed into an aquaculture facility where you boost the temperature of water to grow fish more productively. And the waste heat from that could be sent into a district heating grid to heat the local buildings. So you can integrate to gain efficiencies. And you can design energy systems, overall systems, for better energy efficiency. For instance, cities. You can let cities evolve and develop as they may. And that can be pretty haphazard, hardly efficient. Alternatively, you can look for efficient ways to design. You can locate industries together so that there's an easier cascading of wastes to uses in other industries, and so you leave larger areas of land unimpacted by industrial facilities. You could locate people along transport corridors that are set up for where they live and where they work so that you make mass transit far more easily used and far more efficient and effective than if you just let people live wherever they may develop and may choose to do so otherwise. So you can design systems like communities and cities to promote efficiency, and many communities are trying to do that as they develop. That's number 3, efficiency in a broad sense. 4 is reducing environmental impact. Of course, to be more sustainable, there's a strong environmental part of that, and not impacting negatively or overly burdening the environment is a key part. Thermogram of the the Earth showing temperatures. Of course, there's concern with overall global warming and the temperature rise that on average we see, even though that will be higher in polar regions, north and south, than perhaps in equatorial regions. But on the other hand, the effects in equatorial regions will probably be more pronounced given the temperatures they're starting at, and given many of the situations. So greenhouse gases and associated climate change, one important factor. Using tools like LCA, life cycle analysis, some papers were presented at the conference on that allow us to not just look at a snapshot of how things are operating, but look at the full life cycle to get the full environmental footprint. A better understanding of that are critical. Carbon capture and sequestration, I put it there simply because it's contentious. The dream of the fossil fuel industry, find a way to economically capture and store, sequester somewhere carbon dioxide so they don't need to worry about their contribution to climate change. They're trying. We have a couple large demonstration plants in Canada. It works, but can it be done on the large scale that we need to capture carbon emissions broadly, and can it really hold those emissions permanently, or will they eventually be released? Are big questions. Environmental impact. Lastly, these four are different. The first four items I list there are pretty much technically based. The source and the carrier of energy can be selected, the efficiency and the environmental impact can be assessed technically. But there's much more to energy sustainability, so I put a catch-all, a basket to pull in all the others. Satisfy other facets of sustainability. If we want, the requirements include also other facets. For example, this is a large basket, and I put a bunch here. Where to start? Attitudes. People's attitudes have to be supportive of sustainability, energy sustainability measures if it's to come to pass. If people are against it, they're going to fight. It will not happen. Laws maybe have to be implemented where it's needed to create a level playing field, so it's not just voluntary, but legal standards are set up that everyone has to adhere to. Educating experts about measures you can take for energy sustainability, but also educating the broader public to help change attitudes. Lifestyles and living standards come into play. Nobody wants to give up. Very few people want to give up living standards. Natural tendency is to want more for your children, for your grandchildren, beyond that, and not to give up on living standards. And really, if we're to achieve energy sustainability and to try to do it by saying, we'll go back and live like we did 100 years ago, we didn't use much energy per person, we'll be sustainable. Yeah, maybe you can get a few people to buy in. Probably not that many, and certainly not for the long run. I think we have to accept people want good living standards. In developing nations, they're striving for better living standards, and industrialized nations don't want to give up on those. So it comes into play. We have to respect that. Health is important. Cultures, respecting cultures and their development, not impacting negatively, and also understanding how they fit into the energy picture. For example, Los Angeles. Very broad city, mass transit stinks, and it's very difficult to use. It's a car culture. You drive in Los Angeles, everything, the roads are set up that you get from place to place by car. And on to use the batteries in these as a storage component where the owner of the grid actually reaches agreement with you for a lower energy cost if they have the right to discharge your battery to a certain level when they need electricity back in the grid. You can run appliances off that, lighting, and hook that system up. You can also, of course, integrate the photovoltaic electricity would work its way into that grid. You could add wind to this, you could add other technologies. The idea is there's a large array of technologies that we know how to work with today that can be put together, configured optimally for a given situation to reduce energy use to zero or go to positive energy. We're doing a lot of work in this in Canada. I'm part of a network. It's about a $10 million US network with about 16 universities, 30 professors, and maybe 200 researchers called, and it's a bad name, NSERC is a funding agency for federal research in Canada. Smart Net Zero Energy Building Strategic Research Network. We're looking at using computer controls to operate buildings and communities in the smartest way possible to achieve net zero energy use in those buildings. And this is a strategic research network aimed at with a vision of turning 50% of Canada's building stock to net zero energy within 20 years. A lot of work going on there. The 5 main themes of that, which kind of spell out some of the areas in need of research. And this research project was vetted internationally. We had researchers from Asia, from Europe, on review teams that had to assess whether this gets funded or not. Integrated solar and HVAC, heating, ventilating, and air conditioning systems for buildings, a key area of research to integrate the technologies to get the biggest benefit. Active building envelope systems and passive solar technologies. We have researchers working on insulation for buildings, on window systems that are better in terms of energy efficiency, and all sorts of other passive storage techniques. The area I'm in charge of is, as theme number 3, mid to long-term thermal storage for buildings and communities. A lot of energy use in buildings and communities is heating and cooling. In Canada, it's mainly heating. In other countries, it's mainly cooling, as I said. To achieve net zero means not using fossil fuels. It means using things like wind and solar and geothermal that are not necessarily available when you need them. Without storage, there's no way you can achieve big penetration. There's no way you can achieve net zero. With storage, you can go all the way to net zero. For instance, if you want to heat a building with solar energy, and you try to do that without storage, depending on your climate and how much cloudiness you have and how long the days are, I know in the Toronto area you can achieve about 20% heating with solar. Beyond that, the sun isn't shining at times when you need heating. With the storage component, you can just make it ever increasingly larger until you achieve net zero. Smart building operating strategies is another main thrust there. How you operate buildings, and all big buildings have building operators. Small buildings, it's implicitly there in computer controls. You can change operating strategies to be smarter and more efficient. And finally, we're trying to impact policy and industry. We have a technology transfer research group developing design tools for industry and practitioners and trying to input and influence national policy to move the country towards net zero energy buildings. Some examples to wrap up. I'll start with my university, because it's a very interesting case. It's a new university. We're just over 10 years old. So we had the luxury of being able to build fresh. We didn't have old buildings. We were building from the ground, green field. So this is University of Ontario Institute of Technology. My university, this is the quadrangle surrounded by buildings. We've focused a lot of the building design on being energy focused and positive energy focused. So there's high efficiency, very efficient windows. Under here, for instance, we have borehole thermal energy storage hooked up to heat pumps. So imagine this, and I'm going to take a schematic and look at what's underneath. There's the quadrangle, and that's what's underneath. We have a geothermal heating and cooling system. This is 400 tubes, 20 by 20, separated by about 4 to 5 meters each, going down in the ground 200 meters. In each tube, a hot fluid and there's heat pumps located here. The heat pumps send the fluid down here. In winter, the temperature is warmer in the ground than it is outside. They preheat the air, and then final heaters top it up. In summer, it's cooler in the ground than it is in the air, so the fluids go down and get pre-cooled before they're used. In summer, we air condition. The waste heat from air conditioners gets put in the ground, so it's available for use in winter a few months later, and opposite in summer. So this can store heat in the rock mass surrounding it. It can store cool. Our system actually has quadrants. There are 4 of them, so we can heat up one part of the ground mass and cool another part to allow optimization of the system for heating and cooling when it's required in both cases. Looking at that a little more, this is what goes on in 4 of those 200 tubes. Fluid comes in, goes down, 200 meters, turns around and comes up the same tube. It's a U-shaped tube. So the heat exchange occurs across the wall here. There may be water around the tube or a grout material that conducts well, and the heat basically goes into, this is overburden, shale, and then limestone. Most of what's underneath is limestone here. There may be a water table. You can design around that. But we store the heat or the cool in the surrounding rock mass, and when we want it back, we put, say, a cool fluid through, and the heat is drawn in because the temperature is lower, and we recover the heat and send it back for use. So that's one hole, that's a top view of it. The U-tube is the plastic tube going up and down. 4 are shown here, 200 in total. What's the impact of this? And the economic question always comes up. This was a beautiful system because it made sense, and it is indicative of the typical problem that energy technologies face. And that is, to be efficient, they usually require large capital fund up front, but they pay off by lower energy costs over their lifetime. And that's fine, but nobody ever has the money available up front. Being a new university, we had the money up front. We didn't have students saying, don't spend the money on this system, put it in the classroom. We didn't have any faculty saying, don't spend the money here, put it into labs. So it made sense in the long run, we did it. Savings in energy are about 40% heating costs go down and 16% reduction in cooling costs. Indirectly, there are other savings. There's no need for a boiler plant, so they never bought it. Potable water and chemical treatment, not needed. And rooftop cooling towers and the support, the physical support in the building to support those were not required. So those were additional savings. The payback for economists, the high efficiency part of the system on the HVAC side had about a 3 to 5 year payback period. The well field, the 200 holes going into the ground, about a 7 to 8 year payback period. Overall, the system had about a 5 year payback period. For most business people, that's way too long to wait. Nobody's going to invest money and have to wait 5 years just to break even and then save money after. But for a facility like this in a university that's going to be there for, some universities are 800, 900 years old, a long time, it makes sense. 5 years to recover your investment and then to save, we save about $1 million, and that's what that translates to, for the next, say, 25 or 30 years lifetime of the system. The main challenge, as I mentioned, initial cost. A lot of good energy sustainability ideas cost money up front. Another example is community integrated energy systems. I mentioned I would come back to one. This is an interesting community in Alberta, Canada. Alberta, Canada is in the west side of Canada. It's a province. This is located actually near the city of Calgary. For those who know Canada, that's the fossil fuel center of Canada. The province of Alberta has most of Canada's fossil fuels. But they're still trying something like this. This is an integrated community system. It has homes, two-story single-family homes, each with a separate garage. Solar photovoltaics on the garage roofs. Small solar collectors for domestic hot water on each house. They're all hooked up with a district heating loop. And there's 2 energy storage facilities. Short-term water energy storage tanks for heat, and long-term storage in the ground, like the example at my university. The short-term tanks give you the ability for quick response. Getting heat into the ground takes more time. Recovering it takes more time. So we have this hooked up. There are 52 homes, and those homes are situated in a larger community of 1,000 or 2,000 homes. And it was built. It's been talked about worldwide. There's a picture of it. Here are the individual homes with their solar collectors for hot water. Here are the separate garages with the large thermal collectors, sorry, not photovoltaic. Calgary is located near the Canadian Rocky Mountains, so those are the Rockies that you see in the background. This is a larger community. These are 52 homes on 4 streets, sold in the same way as the other homes. So they've done surveys. People were just as happy in these homes with how they felt versus the other homes. There was no difference. The government subsidized this to make the cost the same because it was more of an experiment. It's done what it was supposed to do. It's achieved 90% solar heating, solar fraction of heating. So they only use fossil fuels for 10%. The designers are looking at Drake Landing number 2, the second phase of this. They said, it was nice, but we could get much better economics if we designed for about 1,000 or 2,000 homes. And so they're looking for that at that now, and the government's considering funding an entire community like this built in a centralized manner. If I go backwards, the importance of the community here is this is shared. Everybody has their own collectors, but they're shared. They support a common storage mechanism for all 52 homes. This can be sized for 500 homes, maybe with different modules to achieve better economics. I was part of, and the perspective is, can technologies do it all? No, there's more to it, so I don't want to leave that out. This is a perspective of one researcher, Drugler, work done in 2012, but it was used as part of the GEA. Some of you might be familiar. Global Energy Assessment was a large energy assessment we published about 2 years ago, the final report after about 5 years of work, done by about 2,000 researchers from around the world under the auspices of IASA, International Institute for Applied Systems Analysis in Austria. And so it was a global attempt to look at global energy use, assessments by country, what needs to be done to make energy use more efficient. I was involved in one part as one researcher. One of the important diagrams that came out that I thought would help here is this. If we simply leave cities develop in a sprawling manner as they do without control, we use a certain amount of energy. A typical breakdown might be buildings using about that much, half, transportation maybe 25%, and losses in the upstream conversion accounting for about 25%. Present system, business as usual. If we go to more efficient buildings, predictions are we can reduce these numbers to about that. Cut the loss down, reduce building energy use, reduce transport energy use. If we design further for compact layouts, so people don't need to travel so far to get from A to B on a normal, say, commute to work, we can push down the energy use even more. Now we're at about 50% of what we started at. Optimizing distribution of energy through district heating and district cooling and other distribution mechanisms allows us to push further and take a lot of the waste heat from these systems and simply put it back in the heating grid to allow it to be used. So we go further. To go the next step, though, policies. This won't happen on its own. It takes government incentives. It may take government support because you have to pay up front, find the financing to build a lot of the technologies. But with integrated policies and support, the estimates were that you could reduce now to about 20% of the original number and get to about the minimum value that they could predict. This was based on a hypothetical 20,000 person community through modeling, but it is indicative of the types of ways we can reduce energy use in buildings, perhaps towards net zero. So in closing, what have I tried to convince you of here? Well, sustainability, critical quest, my starting point that I think the conference is all about. Energy sustainability, I contend, is a key part of that. I would argue perhaps one of the most important parts of it, given the pervasiveness of energy use worldwide. And net zero energy buildings and net zero energy communities can play an important role, given how important building energy use is globally. So that brings me to the end. I thank you for your attention, and I'm happy to answer questions if there are any. If we have time, of course. Are there any questions? Criticisms? Throw arrows if you want.
I'd like to know how long the underground pipes are supposed to last, and what would you do if they break?
Ooh, the underground pipes, they're supposed to be 50, 60 years. If they break, it depends. You can design them for more easy fixing. You can design them for less easy fixing. If they break, the 200 meter down ones, They've got individual sensors on the borehole, first of all, so they can identify if there's a leak, where it's happening. In some cases, if it's a bad leak, they may say it's economic just to cut it off from the system. In other cases, it may be a small leak, they can put some sort of sealant material into it, remove the pipe, remove the actual pipe, and then reseal it. But they do sealant tests up front because they don't want that problem. So they do high pressure tests to ensure the integrity of the system before they go in. But of course, leaks can develop. So they have options, but it can be problematic if a lot of the tubes go. Other questions? Yeah, it was way too fun last night. Yeah.
Thanks a lot, first of all, for the inspiring topic. So just a quick comment. I see that most of your presentation was focused on efficiency, increasing efficiency, and at a very fine scale to community scale. One thing that, although I think is important as well, is to try to cut down consumption where it's not useful. Like, why having to heat up, I can heat up this room with fossil fuels or with solar or with thermal energy. But why, if I can just put on a jumper and it's fine as well. And so, and that is something that I do not know if, with an engineering perspective, you can address. So it's the classic rebound effect, that certain magnitude of consumption you will have. So what do you think about that?
I am in full agreement with you that part of dealing with buildings are tricky. I teach HVAC courses, and they're really tricky because right now we have a certain temperature in this room, and probably 80 to 90% of the people are comfortable, and there's probably a few outliers who are too warm or too cold, uncomfortable for some, just personal nature. And yes, we try to design for kind of the maximum number of people, but we always appreciate there will be outliers. And what we expect them to do is exactly, maybe they'll put on a sweater, maybe we don't need to lower the temperatures as much or raise them as much. So that's already built into designs to some extent. In terms of can we go further and say, well, in summer, instead of 24 degrees, you're going to accept 25, 26, 27 degrees and just wear lighter clothing. Or in winter, we're only going to keep to 19 or 20 degrees. That can be done, but there's a limited margin before people rebel and workers walk out and go on strike, or people are just plainly unhappy. So we can play with that a little, but there are limits. As soon as you start, this is maybe a question that is important for sustainability in general. As soon as you start impacting people directly in a negative way, it becomes a very big uphill fight. One thing I like to do in engineering is do as much as we can invisibly behind the scenes so that people don't need to take actual actions. It's more efficient and more sustainable without them having to accept that they're going to have to wear a bulky sweater in winter, because people are fickle and people will ignore you anyways and complain anyways. But we do what we can within the envelope that's available there.
Thank you. I have a question because here, as you know, in Europe we have new legislation, kind of like the European directives which regulate energy efficiency in buildings, and there's actually a trend to focus first on government buildings or buildings which are owned by the state. So, first question is how the Canadian government responds and how you operate or how you influence all those, I believe, many buildings which are owned by the state. And the second question is if you cooperate with Europe, because this what you are showing here is actually very important for development that we have here.
Thank you for that question. I'll deal with both parts separately and try to remember the second part. Yeah, influencing policy, it's very difficult. We just present the case. We're researchers doing the research, so we're not policy makers. We're trying to inform policy makers. So we're trying to have good, solid work, find a way to make it dumb and understandable in a simple manner so that it can actually be considered at political levels and implemented. The uptake varies. Some communities are really gung-ho. The mayor says, I love that. What do we need to do? We want to take actions, look at our community, assess it, help us plan in our city planning. And we get really good uptake. Others say, I've got bigger issues, it's hardly a priority for me, go away. Or maybe come back in 4 years' time because I'll be out of office and it'll be somebody else you have to deal with. So it varies. We just try to be there continually pushing and continually at least educating. The other main education though is to get through not to the politicians but to the industry, the designers and developers and installers, because they simply like to use the most common, simple tools. Something new is difficult for them the first time, so we want to help them the first time so that it can just be part of their arsenal. And then quite often the clients, okay, do it. If it's just as costly and it's much more sustainable, I'll take that. But if the designers and installers aren't pushing it, it's difficult too. So we try to influence both of them with varying successes. In terms of cooperation, absolutely. We've got partners throughout Europe and Asia. We can't spend money for a Canadian-funded project on them, but they can participate in the project. So that's how it works. Europe and Asia, to me, are wonderful. I'm from Canada. Our energy rates, well, the US has cheaper energy than Canada due to taxation. But our rates are, our rates are cheaper than in Europe. We're about, not quite half, so maybe 60% of the energy costs here. So things that don't make sense economically in Canada already make sense here. So this is my trial bed. I just keep an eye on Europe. These technologies are being tested and the problems are being ironed out so that when it's all ready to use, probably our prices are up enough that we can just buy the most advanced model. But there is a lot of cooperation beyond that.
We unfortunately don't have any more time. Thank you so much. Thank you, Marc. Please allow me to remind you one more time for the two changes that we have for today. The first I announced earlier, that is that panel on irrigation, that water